Exciting. Hi, everyone. Before we start, I'd like you to take a moment to remove your cell phones from your pockets, take a look at the screen and make sure that that the thing that says it's muted is visible and on your screen, because loud noises in the middle of talks are deeply embarrassing, not just for us, but for you personally. So please make sure your phones are on silent. Other than that, please find a seat, and we're about to get underway. This looks good. Oh, and thanks everyone for being quiet so quickly. First presenter in this afternoon slot here on the second day of this PyCon is Hynek Schlawack, who's going to be telling us how to get instrumented. Please make him welcome.
Yeah, hello. It's so great to be back. I'm still Hynek from Berlin. I still work for a small web hosting company called Media. And as every year, I have a lot of material, so we will go straight to it. And let's talk about the goals of my talks right now. And by the end, I want you to be able to predict performance problems. Because stomping out a blaze is a lot easier than fighting a huge operations fire. And if something happens anyway, I want you to be alerted by your system and not by your hysterical boss running into your office screaming at you. And if a fire is burning, there's always some fire at some point. I don't want you to stare at the top output while your boss is poking their finger into your bag, but I want you to have all the data at hand, all the data you need in a meaningful format. And for the post-mortem, I also want you to be able to reason about how you arrived in this particular situation. So I want you to have historic data. And of course, all this should feed back. So if something happens and you need to figure it out under duress, you should get alerted the next time that happens. Unless it shouldn't happen, you should take measures to prevent that. So if you want to reason about situations, you need an objective representation of them. You need ways to express the quality or level of your service. So first, you need an indicator, like the request latency or the uptime. Then you can use those indicators to formulate your service level objectives, like latency must be under 100 milliseconds, 5 nines uptime, you know the drill. So once you have those, you can start writing contracts and agreements and define what happens if you miss those objectives. And SLAs are not relevant to this talk, but SLIs and SLOs are, because SLIs are just metrics, and SLOs are the conditions you want to fulfill, and if they are not fulfilled, you want to get an alert. Now, one step back, what are metrics? Really quick. Metrics are numbers or samples that are time-stamped in a database, and ideally, you have a lot of them, so you can correlate them, because you can read a lot more out of data if you have correlation. Now, you get those time series by adding instruments to your system, just like in a car or in a plane, except that your instruments are hooked up to a time series database that stores them, and it allows for queries and operations on top of them. Now, you obviously have to instrument your app, but also your dependencies like your database, your web server, your load balancer. They all carry very useful information for you to pick. Then you want to instrument your environment, like your server load, your memory, your I/O activity. And finally, you may also want to instrument your business, like the number of your customers or the number of your paying customers. It's not always the same thing. Your daily revenue. Because seeing a graph that correlates your front-end latency with user sign-up rates can be enlightening sometimes. And nothing of this is new at all. People have been doing this for years. I've been doing this for years. I've been even talking last year about that stuff here. But there used to be this problem that in order to get metrics in place, you had to choose multiple systems and decide between multiple options with various trade-offs, which I personally find frustrating and hard if I'm trying to get started with something and I have to start to learn all of them and then decide. And they also aren't really integrated. So InfluxDB or Graphite don't have much opinions on how to get data in or how to do monitoring on that data. They're just storage. And others, like StatsD, and not just I, consider rather broken, because UDP tends to be the first thing that turns to ashes if you are hit really hard with something. And that's even true on localhost. Now, Prometheus is different. Prometheus gives you a well-rounded and opinionated metrics and monitoring system. But it's still flexible, and you can do anything you want, but you have a proven and well-documented starting point, which I personally find very helpful. Now, opinions are a dime a dozen, but in this case, those opinions have some weight, because it's basically a re-implementation of Google's internal monitoring system called Borg, built by ex-Googlers because they were missing their beloved monitoring system in the wild after they left Google. So let's have a quick walk through the architecture. Prometheus is a single binary that you just drop on your server without any dependencies, so you may be able to guess what it's implemented in. And its central feature is the effective storage of time series. So what exactly is stored? A time series is just a named stream of float samples with timestamps. But Prometheus wants you to think of them in terms of 4 types. And the first one are counters, which you can use to count events, but anything else too, because you can increase them by any number. So you can use it to measure your network traffic throughput. But they can only increase. If you want to decrease, you need a gauge. Gauges are used for exposing numbers, and they can be set to anything like the server load, a temperature, or the number of active requests. Now, there's a pretty obvious mapping from those two on a stream of float samples with timestamp. It gets a bit more complicated with summaries that will take measurements, and it will allow you to compute the rate those measurements are coming in, for example, requests per second, and the average measurement. So, for example, the average request time or request latency. Now, some clients, and Python is explicitly not one of them, also allow you to define percentiles, which are then computed within the application, your application. I personally don't find it useful at all, because you cannot aggregate percentiles between, it just doesn't make any mathematical sense. And it adds a server load. If my application is screeching, I do not want it to derive numbers to compute rates. So finally, my favorite is the histogram, which is also about observing values and keeping track of averages. But additionally, you define buckets. And those buckets should have typical sizes for the things you measure. And Prometheus then estimates percentiles from those buckets. Now, I said percentiles twice now. That is because they're so important, and to ensure we are all on the same page, let's have a quick primer on them. So, I will start with a premise, and that's that averages are probably less useful than you may think. And to have something concrete to talk about, let's assume we measure request latencies, and I think it's fair to say that they are an important part of the user experience. So fast requests, good UX. Slow request, bad UX. And it doesn't matter whether it's a web page or an API. They should just be fast. Now, the average time is not the average user experience. Why? So this, not only the average user experience is not 2.8, actually no user experience is 2.8, it also hides the really terrible user experience of one user. And the reason is, of course, that realistic data in production is always skewed to some degree. There are no bell curves in production. And the average just muddles it all together. So That also means that if the average changes, you don't know how many users are affected at all. You just don't know. And it means that you may waste time on optimizing the perfectly good average case instead of looking for the reason of some outlier that's dragging the average completely out of proportion. So, what is the average user experience here? 1. Now, recall high school. There is a function that will tell you that. And this is the median. A median takes a sorted set of values and gives you the middle one, or the average of the two middle ones. Now, the median's strength in representing the average user experience is also its biggest weakness, because this is still 1. But that's not very helpful or useful. So by itself, the median is not useful. But fortunately, where the median comes from, there's more. Which brings us back to the percentiles. They also partition a sorted data set, but this time in 100 parts. And then you look at the nth value for the nth percentile. Or in other words, the nth percentile p is the upper limit of n% of dataset values. Now, this sounds all fancy and complicated, but it's actually easy when you use an example. So, if the 50th percentile of your request times is 1 millisecond, it means that 50% of your requests are done by 1 millisecond. Now, if you think about that, that's actually our median again, which we've already established that is not very useful. But with percentiles, we can look further. We have a parameter to tweak. So how long took 95% of our fastest requests? And now we can immediately see two things. First, the value is obviously an interpolation, because there is no 90,000. And it makes sense because we also don't have 100 values. Now, the more important thing is you see that there's something very, very wrong, that affects only 5% of your users, but it's really bad. With an average, you would think that all requests are kind of bad. But here you see that it's just 1, or 5% in this case. Now, how does such a graph look in production? So, really quick, from the bottom to the top, you can see the median in green at the bottom, the 95th percentile in yellow in the middle, and this squibbly blue thing on the top is the 99.9 percentile. So, you should notice two things. First, the 99.9th percentile is a lot volatile, which is to be expected. It's the slowest per mil of all requests. There's a ton of reasons why it can be slower or faster or whatever. Now, there's also a connection between the median and the 95th percentile. So let's remove some noise. And what do those dents mean? Because they seem to mirror each other. And they mean that the average user experience improved, but the slowest 5% worsened. Their times doubled, or even tripled. And here's one dent that has no equivalent in the 95th percentile. So it means that if it had an effect, it affected less than 5% of your slowest requests. And these are all very useful information when you're reasoning about causes, because you can drill in and you can ask us, and you can think about what could cause these effects. Now, percentiles have two downsides. They are non-trivial to compute, so it's good that Prometheus does that for you outside of the instrumented system. And they throw away most of the data. Like, the median throws 50% away. So averages do have a place, because they sum up the service quality to a single number, including all numbers. So you still need the average, but maybe not for things you thought before. Anyhow, back to Prometheus. And let's talk about metric naming. Anybody who ever used StatsD or Graphite may know these things. They just put all the metadata into the name of the metric. Prometheus, as all modern TSDBs, I have to say, uses bare names. And it's the best practice to prepend it with an app name. This is not a good app name. This is a short app name for my slides, so I can use a big font. And you append the unit. In this case, it's a counter, so the unit is per convention total. If it would be a timer, you would use something like seconds or microseconds, whatever the actual unit is. Now you add the metadata using so-called labels. So each new label combination still adds a new time series or dimension. So you do not get less time series, but it's a lot more readable, it's structured, and much more helpful for aggregations, because you can formulate queries and expressions based on labels, like regular expressions. So where do those values come from? And now it gets interesting, because contrary to most metric systems, Prometheus is pool-based. It means that each instrumented system exports its metrics via HTTP, and Prometheus scrapes them. And using the metaphor from before, you add instruments to a system, and Prometheus comes along and looks regularly at them and writes them down with a timestamp. This is a lot of consequences about which I'd like to talk for a moment. First, it means that you can adjust the resolution of your data, and for each target specifically, because you can configure how often you scrape the metrics. And it's basically a trade-off between the precision of your data and disk space. And the other thing is that if scrapes fail for some reason, like a high load, you do not lose data, you do not lose meaning. You just lose resolution. So your average rates that your metric system tells you is still correct, which compared to if you are sending out samples actively, pushing in them, and they get lost, your rate starts sinking, although the actual rate is rising above capacity. So your metric system is at that point lying to you at the worst possible moment. Now this makes Prometheus great for monitoring, but it makes it rather bad fit for things like accounting, where you need every individual value. In this case, you need something that is specifically made for storing single numbers, like Postgres or InfluxDB. Now, one problem of the pool-based model is short-lived jobs, like backup scripts, because you're not starting to implement your backup script as daemons, so they hang around for long enough and you can scrape them. For that, there's an official push gateway, where short-lived jobs just push their data in, and it's retained for Prometheus to scrape. Now, another problem, of course, is that in order to scrape targets, you need to know about them. This is not a really new problem, because if you want to do monitoring on top of targets, you need to know about them in either way. It doesn't matter if it's pull or push. But of course, here it's even more important. And one way is to just configure it. This tells Prometheus to scrape itself. So it's YAML, as you can see. This will give you the number of time series, the buffer usage, such stuff. And such a metric endpoint is called a target or an instance, and a group of them is called a job. So if you have multiple backends of the same type, then it becomes multiple targets, but one job. And these two things are automatically applied as labels to every metric that is scraped from those systems. Now, in practice, of course, you're going to do something more dynamic. So you will use some kind of service discovery. And Prometheus supports a lot of ways to tell it about its targets. We personally are using console and are happy with that, but others use other solutions and they all work pretty great. So the final problem, and the only actual problem, are closed or netted or load balanced systems where you just cannot expose your metrics. Something like Heroku or end-user appliances in end-user networks. So as for Heroku, I've been taught that there have been talks about a plugin, so it is possible to solve, but nobody cared enough to do it for now, because I think Prometheus is mostly used by people who run their own infrastructure. But other than that, there is sadly no real solution to that. Generally speaking, Prometheus is intended to run in the same network as its targets. Now, some advantages. So first of all, high availability is pretty easy. You just point multiple Prometheus servers at the same targets. Which also means you can just run Prometheus on your notebook and have real production data on your notebook while you're testing. That's useful for playing around or for having interns that you do not want to give the keys to your systems. They can do all the work they need. They do not need access to anything except the metric endpoints. It also means that the detection of outages is a lot easier. Because if a scrape fails, you know something's cheesy. If you are in a push-based system, you have to reason about how long you haven't heard from a system, which is possible, but more complicated. What I personally like is the predictable effect on the infrastructure. Because more traffic does not mean more metric traffic. It just means that more numbers are incremented. So under stress, when monitoring and metrics are needed most, you are not losing samples. And most importantly, the metric system is not a strain, an additional strain to your systems. And finally, instrumenting third parties is fairly easy because most, if not all, production-ready systems expose some kind of instruments. So each database has a special table with performance metrics. Web servers have their status pages. And Java has JMX. So you just have to transform this into something Prometheus understands, which, as it happens, is something you can understand too, because it always also supports a human-readable format, which you can see here. You just point your browser there, and you can read them out. So this is the first part of a histogram called request seconds. Again, terrible name, but big fonts are awesome, so people can read it in the last line. So do not name your metrics like that. And it consists of multiple time series. And the first one is the number of measurements. So how many requests have we seen? And the second one is the sum of the measurements, so the total time observed. So in this case, we had 390 requests that took 177 point something seconds. And this is super cheap to keep track of, because you're just adding float numbers to each other. And these are literally the samples that Prometheus stores together with a timestamp. And by regularly scraping this, it can already figure out the rate they are rising. So you can compute average request times, and this is what you get when you're using the summary type I've talked before in the Python library. If you want percentiles, and you sure do, you need a second part, which are the buckets. So here we have 6 buckets. The LE label is the upper limit, and the counter is how many samples fitted into this bucket. So a sample that fit into 0.5 obviously also fits into 2.0 and trickles all down. And Prometheus can now interpolate percentiles from this. And this is also good enough in practice, and you can always increase the precision by adding more buckets. But you have also to make sure that your values distribute over the buckets, because if all your values are in one bucket, because you chose them on values you would like to have instead on those you have, actually, Prometheus, of course, cannot compute anything meaningful out of that. So now that we have metrics in a database, what do we do with them? We query them using the Prometheus query language called PromQL. And I don't have time for a proper introduction. You can do really awesome stuff with that, like the game of life. But a few examples to give you a taste. So first, if you have many related time series, you want to aggregate them often to one or few numbers. So say you have many backends in multiple data centers. And you want the total request rate over all backends. And we will work ourselves from the inside out. And we take the counter, which you should remember. And to compute the rate, the function needs a so-called range vector, which are the samples of the past 1 minute. And then it depends on the resolution, on how often you've scraped, how many values it actually are. Now, rate takes these values, looks at the first and the last one, and computes the rate out of it. Now you have as many rates as you have backends, and to make it one number, you just sum them up. Now, what if you want to know the rate of the backends in one data center? Then you add a label filter, which looks like this. This will only return or sum up the time series that have the DC label set to west. The rest is all the same. And if you want to see all data centers, but broken down, you drop the filter again and tell the aggregation to retain the DC label using the by clause. So this gives you as many time series as you have data centers. So what else is interesting? Of course, percentiles. Prometheus uses so-called phi quantiles, which completely oversimplified are percentiles divided by 100. So this is the 90th percentile, and we take the rate of the buckets, and histogram quantile will do the rest for you. Naturally, this gives you as many 90th percentiles as you have label combinations, so you will probably want to aggregate them again. Now, we have our percentiles. Once more, these percentiles are interpolations, and their precision depends on how you choose your buckets. Now that we have a slight taste of how PromQL works, let's have a look what else uses it, which most notably are visualizations. The first is the internal one, which is not pretty, but it's not XJS. It's great for playing around, drilling around, query building, and then you just use those queries elsewhere. The downside is it's very simple. You can have only one expression per graph, so you cannot correlate any values. You can build dashboards using Go templates, but there are much better solutions to that. So the best integration still is PromDash. It's the former official one. But since Grafana has merged Prometheus support, it's deprecated, so don't bother. So which leaves us with Grafana. Grafana is the best and best-looking dashboard software right now. I figure many people even just start looking at metrics because they saw Grafana and wanted to have numbers in it. And it has many, many, many integrations, which means that you can build dashboards out of graphs from Prometheus, InfluxDB, and Graphite all at once, which enables step-by-step introduction, which is super useful. You do not have to go all in, so use that if you don't already. So the final piece of the puzzle is alerting. And you can use PromQL to formulate alert conditions, and Prometheus then will push them into a separate daemon called the Alert Manager. And let's take a look at an example again, and let's talk about monitoring for full disks. Once a disk is full, it's too late. But alerting on some random threshold can lead to noise, which in turn leads to alarm fatigue, which in turn leads to 4 AM frustrations. So let's use a crystal ball to be notified in time without noise. And for that, we define an alert that fires when the disk is full in 4 hours. And here's our crystal ball. Surprise, it's more high school math. In this case, it's linear regression. So if given the samples of the past 1 hour, the capacity is below 0 within 4 hours, and this condition is true for 5 minutes, we want to be alerted. Now, how you get alerted depends on you. The Alert Manager integrates with a lot of solutions. You can have email, PagerDuty, webhooks, Slack, whatever you want. And the very final part, how do you make this web scale? And the answer is federation. So Prometheus servers can get their data from other Prometheus servers. So the typical use cases are aggregation, where you have one Prometheus server per team or per topic, maybe one for infrastructure, one for applications. And there's one big Prometheus service that just sucks all in and aggregates this data. And you can also use it for downsampling, where you have one server that has a very high resolution for a very short time, and then another one which samples this data down, but has a very long-term storage. So now you have a general idea on how Prometheus works. Let's focus now on how to get data into the system. And there's a lot you can do without touching your actual code, so there's where we will start. And Prometheus is public for something over a year now and has had a very active ecosystem. And I've already mentioned that it's very easy to build integrations and exporters. So there's a lot of first and third-party exporters available, including bridges, which means that you can point existing instrumentations at them and let them scrape by Prometheus. So if you have a perfectly instrumented app that uses statsd, you can leave it for now and still have the benefits of Prometheus and its alerting. Now, native is better, of course, so let's start with platforms. And for fully featured servers, Metal, KVM, LXC, you are going to use the first-party exporter called Node Exporter. It instruments systems from the inside. It runs in the servers. Now, you know what comes next? One process containers, like Docker, use CAdvisor, which instruments from the outside using container APIs. And once you have these in place, you have already full system insight, server load, number of processes broken down by status, so you can tell how many processes are actually running, waiting for I/O, sleeping, your free memory, network saturation, the disk fullness, as we've seen, very useful, and of course I/O, if your servers are screeching. So installation of those should not be something you do, it should be something that happens automatically as part of a provisioning process. Another non-intrusive method is mtail, which is really cool because it will follow a file and it will compute metrics on the fly based on regular expressions and a special DSL. So in some cases, like the Apache web server, you can get better metrics through a custom log format than you get from its status page. So something you should definitely check out. And no matter whether you go to the status page or the log file, you should always instrument your outer edge of your system and your infrastructure, which usually means a web server or even better, a load balancer like HA proxy. Now, if you want to look at your app from the outside, there's also several black box exporters, which means like for developers pingdoms that will probe your system by pretending requests and will derive metrics based on them. Downside, of course, it creates additional load. Then all kinds of databases have all kinds of metrics. You should all look at them. And of course, if you run your own infrastructure, you should be collecting SNMP data. So at this point, we have detailed information about our platform. We know how to look at our app from the outside by analyzing its logs or by probing the systems. And we know that or how we can instrument third-party applications. That means, assuming that you really instrument the edges, that you can already correlate request times with various platform metrics and dependency metrics, which is already pretty good and useful. But we want to drill deeper. We want more information. So, and for that, we have to touch your code. And to make things interesting, we'll use an example, which of course contains cats. So, let's assume you've built a groundbreaking product, software that determines whether a photo contains a cat. Now you need to deploy it as an HTTP service, where the user posts a picture, and you reply with meow or nope, depending on what the picture contains. How hard can that be? You just build a Flask web service. And you don't need to understand Flask or Python for the matter to get what's going on here. You just check authentication, and because your colleagues read Hacker News, it's a microservice written in Go, and we have an expensive computation that determines the actual contents. So I bet lots of you have already written APIs like this, so let's instrument it now. And for that, we use the official Prometheus client package. So, and before we change actual code, we do the least we can do. We just start the HTTP endpoint off from the client. Because on Linux, you get process statistics for free, which means you get your memory usage, you get your process creation timestamp, you get your CPU time, and you get your open file descriptors, and the the maximum number of open files. So without further action, you can already detect memory and file handle leaks, which are pretty hard to find otherwise, and you can monitor whether you are approaching the FD system limit. So this is, again, another step. But let's start really instrumenting now. And for that, we defined some metrics. So first, a histogram with the request latencies, then a histogram with the picture analysis time, and finally, a gauge with the number of active requests. So let's add them to the app, and we do that just by adding those decorators that do exactly what they sound like. The upper one tracks how many function calls are in progress. In our case, that's the number of requests in progress. And the other one times the calls to this function. Now, you might be saying that a middleware would be better suited for this purpose, and you'd be completely right. But writing Werkzeug middleware is kind of scope. So please indulge me. Additionally, we measure the time to analyze, to find out how big impact the actual computation even has. Because for all you know, all the time sinks into authentication, which in turn, ostensibly, is not instrumented, because it's a shared package. So let's instrument that package. Because if you use something 10 times in an app, why instrument it 10 times? So again, you define a metric for the time spent, and one for errors. Now, I said that authentication is a microservice, which makes it a distributed system, which means it will fail in hilarious ways. So, if it fails, we count it and retry. And again, I know this is not the proper way to retry in distributed systems, so please cut me some slack. So, if this rate goes up, you have a problem. And you know it right away, independently on how well instrumented the other system is. And additionally, we also instrument and count the number of wrong credentials, because those are a red flag too. It can mean you're under attack, or it can mean that your authentication server is failing in a very subtle way, which manifests itself in wrong credentials. It all happened before. So these names are the same for all applications, and you would differentiate those metrics using the job label or the instance label. Now, if you do everything properly, you instrument your shared libraries, you put web-related metrics into middleware, or even better, into whiskey containers, you're left with one extra line in your view, which is A, tolerable, and B, you should not be ashamed of instrumentation. Basically, any production-ready software has instrumentation code. So yours can have it too. It pays off eventually, and nobody ever regretted to have too much information when they were analyzing some weird failures. Now, you may be asking, what about async? Or maybe not, but I did, and that's why I wrote Prometheus async. And it supports async I/O and twisted, and does just the right thing with deferreds and coroutines, by simply wrapping the metrics from the official client. Because I don't want to do math, and you don't want to make math either. Nothing good has ever come out of that. So, additionally, a few goodies. An AIO HTTP-based metrics explorer, which is more flexible and more configurable than the one that comes with the official client, which also can run in a thread, which means it's useful with any Python 3 application. So I use it with my pyramid applications. And it does auto-registration with a console agent. But service discovery support is kept generic, so whatever you like, it can be easily integrated. OK, so I believe everything is instrumented from top to bottom. So let's wrap up. And let's look at the promises I've made. First, prediction. If you have dashboards and look at them, you can probably predict something. But you have also really nice functions like predict linear, or the even nicer hold winters function, which just landed it 2 releases ago, which allows you to put different weight on newer or older samples. So this is done. Alerting, there's a whole system, the alert manager. It has many integrations. PromQL is super powerful and super useful to write sophisticated conditions. That's done. And holistic overview, you needed it already to implement the first 2. So yeah, if you instrument widely, you have the data. You can build dashboards. You can play with PromQL if something goes wrong. You've got everything you need if shit hits the fan. So we've covered everything. And I hope you're eager to measure all the things. Please study the talk page, because, again, I have to skip a lot, or skim over a lot of things. It contains all the links and all the projects, as always. And yeah, follow me on Twitter, get your domains from Media if you speak German, and that's all I had for you today.
Oh, thank you very much for that. Hynek won't be taking questions. If you'd like to speak to him about the material he's spoken about, I'm sure you can find him up at the front of the room in a moment, or out in the hallway. Please thank him again. The next talk in this room will be Russell Keith McGee talking about Python on cell phones at 10 past the hour. See you all then.